Hello everyone, I'm Zheng Panpan. I come from China, Shanghai Tech University, and Shanghai Institute of Applied Physics. This report topic is the magnetic system conceptual design of an 11 MeV isochronous superconducting cyclotron for radioisotope production and its upgrade. This topic includes my previous design in China and recent months' results under the guidance of my supervisor Oleg in Russia. This report includes first of all, I will introduce all the features of my design and followed by the specific design process, include magnetic system design and beam dynamics calculation, central region configuration extraction system, and upgrade the cyclotron and problems in current plans in the future. First of all is the introduction. This cyclotron is a 3 spiral sectors compact superconducting isochronous cyclotron. It will accelerate the H- to 11 MeV and extracted the proton beam by stripping foil. We isolate the initial answer, PIG answers with initial beam energy of 20 eV. The extracted beam energy of 11 MeV with beam intensity of 50 microampere, aimed to produce the radioisotope. My primary task include modeling the magnet system using SolidWorks simulation static electromagnetic fields using Opera and CST, performing the beam dynamics calculation with OPPO and DANS. Table 1 is basic cyclotron parameters. The next part is magnet system design and beam dynamics calculation. The first step of my task is establish the magnet system. Figure 1 is the 3D models up the upper half of the magnet system, and this is RF system. The figure 2 is the magnet field map in the medium plane calculated by Opera. This map satisfies the isochronous condition, the central magnet field of 3 Tesla. Figure 3 is the deviation of magnet field from isochronous. The green line is the isochronous error in the map, so we can see that the isochronous error is below 10 Gauss within the accelerator region, but we can see that in this region there is a big error, big isochronous error. So it means that there is a negative gradient of the magnetic field. It will provide vertical forcing for the beam. Due to the initial beam energy is very low, so the isochronous condition is low critical compared to the vertical focusing for the beam. So this isochronous error can be acceptable in this region. By the way, this region is called the central region. After we obtain the isochronous field, we need to perform the beam dynamics. In order to verify the isochronous field, the static analysis is conducted. Figure 1 is the equilibrium orbit distribution energy from 1 MeV to 11 MeV. we can see that the orbit exhibits an approximately centric distribution, and the beam will undergo small oscillation around those orbits. Figure 2 is the twin diagram. This is calculated by Oppo and Cord. Cord is read by Oleg. We can see that the difference between the results is negligible. We can see that the working point doesn't pass through any dangerous resonance line throughout the accelerator process. Single particle tracking is performed by Oppo and Dance. Oh, sorry. Figure 1 is the trajectories of reference particle. We can see that the particle is a non-uniform distribution, indicates that I have a poor beam centering. From Figure 2 and Figure 3, we have the results as follows. The beam energy is up to final beam after accelerator, the turns of 191 at a radius of about 155 millimeter. The energy gain per turn is about 56 MeV throughout the accelerator process, and the difference between simulation results from Oppo and Dance below 1.5%. The phase slip is within 6 degrees, indicates that we have a good isochronous condition. The next part is central region design. Central region design is a critical design in magnetic design. Due to the initial beam is very low, so the central region design significantly affects the intensity and quality of the extracted beam. So a good central region design should have maximum phase acceptance and high beam transmission efficiency, and providing sufficient focusing for the beam. Considering these aspects, the central region configuration is shown in the Figure 1. This is the ion source and polar and phase selector. The D angle of 197 degrees, radius of 180 millimeter. We accelerate the particles using first harmonic number RF frequency of 46 MHz. The maximum voltage of D is 30 kV. The ion source is located at a radius of 7 millimeter. The beam will emitted from here and undergo circle motion driven by the electromagnetic fields. Why we choose 197 degrees? Figure 1 is the RF phase at each gap throughout the first gap and 3 gaps throughout the first 3 turns. From this figure, we can see that the electric fields will give the beam focusing at the first gap and defocusing in the second gap. In this case, the transmission efficiency of central region is 27%. In order to improve this efficiency, we change the angle to 197 degrees. In this case, the electric field will provide focusing force for the beam at each gap in the first 3 turns. In this case, the transmission efficiency of central region is improved from 27% to 62%. why we add a phase selector in the central region. This figure is the energy gain of particles and trajectories with different initial particles. We can see that from those two pictures. Particles with initial phase between 0 to 30 degrees has less energy and bad beam centering, which lead to the bad extracted beam quality. So we add a phase selector in the central region to delete those particles to enhance the extracted beam quality. The transmission efficiency of the central region is 62% with only 75 achieving accelerator, the 11 MeV without the phase selector. This figure is the phase acceptance of central region. The blue dots is the initial particles phase distribution from minus 90 degrees to 90 degrees. Red dots is accepted particles phase distribution. We can see that the left side is the phase acceptance without phase selector. The right side is the phase acceptance with phase selector. Currently, the central region configuration with the RF phase acceptance around 35 degrees. This figure is the particle loss in the particle loss configuration. The gray dot is the particle loss. We can see that the particle almost lost in the central region phase selector and in the first few turns. The transmission efficiency of the central region is 50% with 30% capable of accelerating to the final beam with phase selector. The next part is extraction system. The beam is extracted by dual opposite stripping foil device as shown in the figure 1. There is a stripper 2 and stripper 1 and stripper 2. The H- will lost 2 electrons by stripping foil. Most of the beam will extracted by the stripper 2, and the rest of the particles will discarded by the stripper 2. The transmission efficiency of the extraction system is 96%, and extracted beam energy is 11.12 MeV with energy spread of 9.8 keV. The next part is upgrade the cyclotron. First of all, why do we need to upgrade the energy to 18 MeV? From this picture, we can see that the extracted radius of 11 MeV about 160 millimeter. For 18 MeV, the extracted radius about 200 MeV, 200 millimeter. The sector radius of 11 MeV is 250 millimeter. So there is a sufficient space to upgrade the extracted beam energy to 18 MeV. The reason too is an 18 MeV can produce more current and higher yield of isotopes compared to the 11 MeV cyclotron. This is a comparison of two models. The left side is the 11 MeV cyclotron. I obtained the isochronous field by adjusting the magnet height in the valley. in the valley at different radii. The right side is the 18 MeV cyclotron. I adjust the sector width obtain the isochronous field. I think this method is simpler and more feasible than previous approach. And the current density is also decreased from 170 ampere per square millimeter to 90. The total current is also decreased. In order to provide a sufficient space for RF system, we must introduce the vertical gap between hills from 30 millimeter to 50 millimeter. 30 millimeter to 50 millimeter. In this figure, the green line is the flatter of gap of 30 millimeter. The black line and blue line is a gap of 50 millimeter. We can see that the flatter will rapidly decrease when we increase the gap. It can be acceptable, but we also slightly increase flatter by using adjusted spiral angle of sectors. Figure 1 is the spiral angle verifies the radius. The blue line is the optimized result. We can see that the maximum spiral angle decreased compared to the previous design. I think it is good for engineering and maintain zero spiral angle within the 0 to 10 millimeter radius region to enhance the flatter. From this figure, we can see that the black line is higher. The blue line is higher the black line, so the flatter increase with the radius region of 0 to 200 millimeter. This is the working point analysis. Figure 1 is the radial and vertical Baitron twins verify the radius. The green line is the optimized result. We can see that in the central region and this region, the vertical Baitron twins has a significantly increase in this both region. It was noting that there is the radius Baitron is below 1 in this central region, but due to the trajectories, radius will rapidly increase in the central region. So the beam will pass through the resonance line mu r equal to 1 quickly, so it can be acceptable in the central region. The next part is problems in the current and plans in the future. The problem 1 is optimize the ion source position. Figure 1 is the evolution of radius circular center during the acceleration. The circular center will start from here and deviates from the geometric center of the machine is here. Indicates that we still have a per beam centering. And the figure 2 is energy gain at the H gap. We can see that there is the energy gain is not good in the first initial photon, so we need optimize the ion source position and the parameters of initial beams to optimize those results. The problem 1 is Lorentz dissociation. We calculate it for 11 MeV. The simulation results is shown in the figure 2. We can see that only six particles are lost due to Lorentz dissociation with an initial particle number of 10,000. So from this result, the Lorentz dissociation doesn't take into account for 11 MeV. But for 18 MeV, according to the formula, we can see that the fraction of dissociation is 0.04% at 18 MeV. So from this result, I think we need to calculate the Lorentz dissociation for 18 MeV cyclotron. Okay, that's all question and answer.
Thank you. Have you any questions, dear colleague? Да, конечно.
Two diagram. Twin diagram, okay. Yeah. Oh. Yeah. Yes. This is twin diagram. Yes. Equal. Yes, mu r equal 1 is qr equal 1. This resonance line in the central region, the working point will pass through this resonance line, but we think it's okay.
Question. What is called the information of magnetic error of field magnetic
Magnetic?
rated of radiation.
Sorry.
Error of field magnetic field.
Error.
Or maybe calculation of particle rotation frequency from radius.
You showed already
Oh,
previous slide.
previous also.
Она показывала.
Oh, this.
Зеленая, да, зеленая. Green line, yes?
Yes, green
Deviation
line
of
is-
mean magnetic field from isochronous.
The maximum.
No. In the region of the synchronization, approximately plus minus 10 Gauss, green cool.
10 Gauss,
10
within
Gauss.
acceleration.
Yes, 10
So,
Gauss, 10
yes.
Gauss. Yes, 10
10,
Gauss.
10.
10 Gauss in this region. The beam will extracted at the black line. Yes.
And
You're welcome.
I do not understand clearly. You have two models for
Yes.
11 MeV
Yes.
and for 18 MeV.
Yes.
They are different just in isochronous field or some dimensions of the magnetic structure. Diameter of the magnet, diameter of the coils, are they the same in both?
Not same.
Not
Because we increase the vertical gap of the between hills.
same. And how much they differ in diameter of the magnet, for example? Diameter of the magnet, as of the yoke of the magnet, in the accelerator 11 MeV I saw in the table, and for 18 maybe I missed diameter. It was in the very beginning.
This.
You show.
This.
Oh, here. I see difference in coils, but is there difference?
Totally
in-
different.
Huh?
Totally different.
Repeat, please.
This design totally different with this
What's
design.
the size of the yolk?
The yolk,
Diameter of the yolk for 11
For
MeV
both.
and for 18 MeV. How much?
I forget it. I will show
But
it.
big, small, how much? Approximately difference. As the sectors differ,
The sectors is same. Sector radius is same.
sector are different and the same diameter increase, yes? The same value as sectors.
The sector radius is the same, but the coil diameter is different. Same. It's not same.
Yeah. Okay, thank you.
You're welcome.
And the level of the magnetic field, mean magnetic field, is the same in the both models, yes?
No, not same.
Not same.
Yes.
Is it smaller for 18 MeV? Because I'm thinking about Lorentz.
Lorentz distance.
Yes. You said that you need to look at it more carefully, yes?
Yes.
And there is no problem in 11 MeV cyclotron with this effect, and for 18, I just asking because to understand how much smaller magnetic field for cyclotron, for the second cyclotron, for the 18 MeV cyclotron. Is it really smaller? Or
The magnetic field in the central region is is same.
is the same?
Is same. About size 3 Tesla
Yeah,
in
I
both
see.
models.
Now I see. Thank you. Any other question? Someone else? Ты последний задашь?
Я последний вопрос.
Давай. Please.
The proportions for
Equation.
Yes. Represented. 2-4. Is down.
Say a few words about code OPAL.
Code of
What equations they use. Это известный код. Это лучшая программа мира. Это PSI.
code OPAL is a PSI code.
Она использует OPAL прежде всего. И там, конечно, полное уравнение движения. Да, конечно. Да, она все тестирует OPAL. Где-то что-то свое пишет, но все тестирует OPAL.
You're welcome.
It was last question, so we thanks you again.
Thank you.
Всем спасибо. Было очень интересно.